Our next speaker is the founder and director of the Touch Lab at MIT, and he has been for the last 20 years. His area of study is haptics. Can anyone tell me what haptics is? Touch. Anything to do with touch. A good thing for the director of the Touch Lab to be involved with. And the way the word haptics is used now is actually based on his earlier papers, so he's even made a contribution to the English language. His interest is in human and machine touch and the interaction between the two. Will you please join me in welcoming Dr. Mandayam Srinivasan to the stage?
All right, thank you. Thank you very much. Can you all hear me? Okay. Okay. So, I am a kind of mechanical engineer turned neuroscientist turned roboticist. So coming here, and I have never been to an AI conference before, so coming here I feel like Alice in Wonderland, as puzzled as Alice in Wonderland in various issues and, kind of worries about all these information processing machines exceeding human intelligence when in our mechanical engineering labs, it's so hard to make even these dumb machines work, So it is hard to imagine, but I can see that viewpoint, and we have been succeeding as well, though not at the same rate. So I will talk about some of those machines. To start my talk, since we are already late. Okay, so I titled it Enhancing Our Bodies and Evolving Our Brains. And of course, I need to introduce haptic interfaces, because that's what I work on. How to become superhuman with haptic interfaces. That is going to be the subtext of my talk, and hopefully you will agree with me. So humans, what I want to focus on my talk is the interaction between humans and machines. So as I said, our robotic machines are pretty dumb still, in spite of 50 years of work, and we still have large limitations on our actuators and sensors and so on, even though the information processing part is improving. So what we think that will work in the near future, or at least for the next 10, 20 years, is human in the loop. That is, human and machine working together. So in fact, the last talk, it was good that I followed the last talk, and the fact that it also happened to have some MIT in it has, we have not sponsored this commercial session by MIT, okay, just coincidence. So we want to do this interaction, and that I want to claim is that there are new interface technologies that enable superhuman capabilities, and I'll define what that is in a short time later. Then physical interaction that is not just optical. I mean, for example, what my previous speaker was wearing is a kind of optical interaction. So I'm talking about physical interaction where you can touch and feel things. You can apply forces on the environment. Physical interaction, I claim that not only enhances the body, that is, you can have superhuman capabilities with those technologies, but also is important for brain modification and evolution. So then it's true that this kind of interaction, of course, can happen even without haptic interfaces. I suppose with modern technologies, you can have eyes directing some robot that's applying some force somewhere. But since this is a neglected area, so I want to emphasize that haptics and active touch is an essential component for some of these immersive human-machine interactions. So there are various levels of interaction. I'm going to talk about 5 levels of interaction here. Interaction level 1 is just us exploring the real world. So we are here, so there is our brain. And then you have, let's say, vision, audition, touch. You can put other sensory modalities as well. Then once you start exploring, whether through your hand, it can be through your eyes as well, then you have essentially established a closed loop. That interaction is important for the brain to develop and for us to do things better. So there is a closed loop sensory motor interaction that happens even during exploration, which is typically low energy and typically just for information to the brain. You can't change the world with it, but you can learn about it and you can sense it and you can plan or run simulations on it. So what I want to, but this is quite useful in itself, this first level of interaction. So in order to illustrate how useful that can be, I want to bring to your attention this method called Tadoma. Basically, this person, Nat Derlak, my colleague, is a person who has hearing and vision and everything all normal. But these two people on his side, they are deaf and blind. And they became deaf and blind when they were about 1.5 to 2 years old. But they were at least fortunate enough to learn a system called Tadoma, where they put their hands on the mouth and the throat and the cheeks of the speaker. And with training, they can understand speech at normal speeds just through their hands. Okay? So this is followed by a video where on the right you have a deaf and blind person, and on the left there is an experimenter. And the video is digitized from an old VHS tape, so it may be a little noisy, but still I think it is understandable. So the deaf and blind person is conversing with the experimenter, and he is hearing the experimenter only through his hands.
When I talk to a children, it's very, very difficult because you don't talk to kids very often, maybe once a month. So, you put it must be, if I don't talk to people for another 1 or 2 years, it would be so rusty that I could not understand anybody anymore.
Oh, I hope that doesn't happen. I hope that doesn't happen.
I hope not, but
You say it feels different to listen to children?
because children have hard voice and don't always speak plainly sometimes.
Okay. So that was completely through touch. That is, he was able to understand speech at almost normal speeds. In fact, a side story is that he came to our lab and he put his hand on me when I was speaking, and he asked me if I was Indian. And that's a true story. So you can even recognize accents, and if you are trained enough. Okay. So now what's happening there is that, so I guess most of you know that there is this homunculus, which is the representation of the body in various sensory cortex areas. So this is in the somatosensory cortex, which is related to touch. So each part of the body has a representation there. And so it is distorted because the thing is, for example, lips and fingertips have much higher sensory resolution and sensor density compared to, for example, the back. So that's why you have that distorted picture of the human. That's how it is represented. And what happens to these Tadoma trained people is that when they don't have the visual inputs and the auditory inputs because they are deaf and blind, the touch areas expand to take over, much of them, and their sensory homunculus would look very different. So similarly, for example, we could also train ourselves in the Tadoma method, and after 10 years, we would also be, it's not like they have any higher spatial resolution. It is just that their brain is trained to parse the signals that are coming from their sensory receptors in the skin and is able to interpret it as speech and understand it. So if we know what kind of signals we can put into the human with the right bandwidth, right resolution, and so on, and if we train appropriately, amazing things can happen. So let me go to the next level. So that's level 1 is that interaction, and that feedback loop can have amazing consequences. Now, interaction level 2 is manipulation of the real world. So what that is, that also is a sensory motor loop. That is, you have sensory inputs coming and you act on the environment. But the goal here is not to learn about the world, but the goal is to modify the world. So this is, you apply typically larger forces here. So there is an energy exchange and there is mechanical work typically. But this is the only way that we can modify naturally the world around us. Now, to go further, what we do is we use tools, of course, and this is what distinguishes us from most animals, and certainly we are very good at it. So in terms of from building the Golden Gate to a space station, whatever it may be, what enables us to do it are these tool interactions. So we are able to build specific tools, and through them we are able to operate on the real world. So therefore, they extend the capabilities of our bodies. And it is true, as we use the tools, there is some sensory modification of the homunculus. So there is a modification of the brain. But these are what we think as evolutionary changes, small changes, not radically different changes. Now, what I want to talk about is new technologies, which are also essentially tools, except that they have information processing built into them. So I want to focus more on these immersive interface technologies, which basically, and I claim they enhance both our body, which means our ability to do things, our resolutions, our reach, and so on, but also to enhance our brain capabilities. So let me give you some examples from our own work. So here is one device which we have used, which is a haptic interface, which is a force feedback device. So there is that robotic device which has a pen attached to it. And I can program any kind of objects. I mean, like this. This is a banana. This is a donut, and so on. I can program any kind of shaped object. I can put any texture on it, any friction on it. I can make the object soft or hard. But these are all virtual. The objects do not exist in the real world. But what happens is when I move that stick. Oh, sorry. Let me go back there. When I hold that hand, I can explore each of these objects. The way it works is, suppose, let's say I have a sphere. I want to program a virtual sphere. So I'm holding this robot. As I move in air, I encounter no resistance at all. So it will be like in the real world. But as soon as I hit this virtual surface, I turn on the motor, so they resist me. So then I can recognize that there is a resistance, there is a surface. And if that force vector is perpendicular to this surface at every point, you will recognize that it's a sphere, smooth sphere. Okay? So that's how it works. So we have used this force feedback device called the Phantom in many situations. There are mainly two classes of applications for this. One is in terms of virtual reality. So that is basically you interact with computer-generated environments. Just like you have your computer screen that displays your visual images, which are actually purely computer programs, but your brain understands as real images. Similarly, the Phantom device can translate your computer programs into touch and feel of objects that you recognize. Okay? So the way it works, again, let's look at how, for the moment, ignore the right part. And let's consider you have a stick and you are touching a real object. Forget the machine, that's a real object. What happens is forces are imposed on the object, and that causes, the forces are imposed on the skin, that causes the receptors to respond. Your brain then recognizes that you are touching an object and its shape and texture and so on, and then it commands your muscles, which changes these forces, and this is how you do an exploration or manipulation of the object through touch. Now, in order to make a virtual or a programmable object, what we do is we replace the real object with a robotic machine, like the Phantom. It has sensors and it has actuators. And as I said, as I move in air, if it's not touching, if the tip is not touching the object, then nothing happens. So because there are sensors here, so the computer knows that you are just moving in air. But as soon as you touch the surface, the computer knows that, and then there is a model of the object, whether it is soft or rough or whatever it may be. It commands the motors to resist you appropriately, and therefore you can feel the object. So this is how the virtual haptic interaction works. Okay? Now, that's one context. And there are multiple applications of this. We have worked on, say, for example, medical trainers. That is, just like flight simulators are used by pilots, you can have surgical simulators. You can have minimally invasive surgery training where you don't have cadavers at all, where you would actually operate on a virtual body. And it can even be, in the future, surgical rehearsal. That is, each body is different. So before a surgeon operates on a particular patient, the surgeon could have all the data about that person and could actually plan the surgery by operating on the virtual body and then do the real surgery. Okay? That's all possible. Now, other applications, of course, are we are developing some sort of aids for blind individuals. For example, you have Google Maps and Yahoo Maps or whatever it may be, where you know what the place looks like before getting there. Similarly, we are developing three-dimensional models of, let's say, a museum a blind person needs to go to. Then he or she can actually feel where the steps are, where the door is, where the information kiosk is, and so on, and plan a route. And their GPS device can actually guide them in situ. So these are all devices, systems that will come on in the near future. Now, there is another mode in which we use haptics, which is in teleoperation. Earlier, the virtual reality is you are interacting with a computer program. Here, you are actually interacting with the real world, but it is mediated by computers and programs. Okay? So, for example, this part is still the human loop. That is, you are holding this, and your brain is getting the sensory information, and it is moving the hand. Okay? But then there is this machine, which is the haptic interface. Same interface will work, but that computer is now connected to another robot. So the motion of this robot controls the motion of this slave robot. This is called the master. That's called the slave. And, oops. Okay. So when you move this, it can control that robot. That robot can actually touch a real-world object, and the forces that are sensed by this robot are transmitted back and hence to the human. So you can have action at a distance. It can be across the room or across a continent. And for example, there is already a system for telemedicine, for telesurgery called the Da Vinci system, where surgeon can operate the master device, which in turn controls a robotic device, which is a lot more precise than the best surgeon can be. So we can even filter out tremors if needed. You can do beating heart surgery and so on. It gives you capabilities that you wouldn't otherwise have. And I'll also describe another project, which is nanomanipulation, where humans can be operating in human scale, but the slave robot can be operating in nanoscale. Okay? So now let me discuss about, I think, 4 examples of what I call superhuman applications. So one is haptics for virtual reality and haptics for teleoperation, and some of it is combining the two. Okay, this refers to something that we did in 2002 in collaboration with Mel Slater of University College London, where we demonstrated touch across the Atlantic. That was the first time that was done. And the way we did it is, let me go to the next one. So the way we did it, we had a phantom device in my lab at MIT, and Mel Slater had a similar device in his lab in University College London. And together, we were able to we programmed a virtual cube, which is shown in here. And you have 2 cursors. One cursor corresponds to me, the other cursor corresponds to Mel Slater. And together, we could touch and feel the virtual cube, lift it, and put it back. So it was a very simple task. But just to demonstrate the principle that one could do it, and we used NSF's Internet 2 at the time. So let me see if it will play the... No. Okay. All right. So we were able to accomplish this touch across the Atlantic, but there were time delays. One of the inherent limitations is even if signals are transmitted at the speed of light, even suppose you don't take any other computational delays into account, there will be a 100 millisecond or so delay, round-trip delay between Boston and London. So it'll be unstable in the sense that the force that I am sensing now that Mel Slater had applied, that's 100 milliseconds before and vice versa, and that causes instabilities. So for that, you need some predictive algorithms in order to minimize it, which we have now. But still, there is going to be an inherent physics limitation. That is, that you will have time delays in this teleoperation, and that causes instabilities. Now, the next application, which is again a teleoperation application, is something that I started last year in Europe, is that you have, again, a master device, and that in turn is controlling another slave robot. But the slave robot is few centimeters in size, but its resolutions are in nanometers. Okay, so it has a micro gripper, as it's shown here, and it can operate certainly in micron level and eventually in nano level as well. So the idea is that you should be able to be immersed in a micro world initially and eventually in a nano world by having all these interfaces. You have a haptic interface, you have visual interface, and you have sound too if you want. And at least at micron regime, optical systems work, the microscopes work. So you can be immersed and you can basically operate at micro level. Say, for example, you should be able to do cell surgery fairly easily because cells are typically like 20, 30 microns. You should be able to do blood, red blood cell, which is about 5, 7 microns or so. So you can go finer and finer, but there are interesting scientific questions there because as you go to finer levels, gravitational force is no longer the dominant force. You have adhesive forces, surface tension, van der Waals forces, and so on. And that completely changes the dynamics of interaction. So you need to be able to model that. For example, one of the big problems we had was that whenever you grabbed something, it stuck to the gripper, and you could never get rid of it. And so you had to use some coatings, hydrophobic coatings, hydrophilic coatings, and so on. So lots of things just to do a simple, what you would do in your kitchen so easily that it is not so easy in the micro world. And nano world also, it is even more difficult because you can't see what you're doing. So you will have to, especially if you want to do live kind of work, then you can't do scanning electron microscope. So you have technologies that need to be developed. There is TED microscopy. Some things are coming in, but there are issues there as well. Then there is another project that I am involved in, which started in Europe, which is called beaming, and basically from Star Trek, the same concept, except that we do not disintegrate people and then reconstruct them. So we are not able to do that yet. But we have a workaround. And basically, the idea is that, let's say I am the visitor. I am going to another location where there are locals, there are real people. So I will go into a room here, which will be full of sensors. And also, I will wear an exoskeleton. I'll have a haptic interface. And I will be represented at the other end by a humanoid robot. But the people, locals there, don't see it as a humanoid robot, but see as me because they will be wearing head-mounted displays. Okay, so which means that I am controlling that robot, and the robot appears to them as me, and then they will have physical interaction with that robot, which will have force sensors, which will be transmitted back to me, which actually I can touch and feel where I am. So this is an extended way of teleconferencing, but where you are physically there and they are physically interacting with you. So this is a project that multiple nations are. It's fairly well funded. So we hope to achieve that in the next 3-4 years. This goes back to a project I did with Miguel Nicolelis at Duke around year 2000, almost 10 years ago, where for the first time we demonstrated how you can control robots directly from brain signals. So, for example, even again going back to Star Wars, there is this scene where Yoda just moves his finger and then lifts a whole spacecraft out of the marshes, and this is supposed to be amazing. But I claim that in principle, we have shown it that it can be done. It's not so amazing. So here is how it worked. How it worked in our case. Okay, in principle is the key word. So the monkey at Duke had basically, let's say it was feeding itself or moving from point A to point B. And the commands for it mainly comes from its motor cortex, primary motor cortex, okay, which is in the front here. And Miguel and his collaborators basically developed an electrode array which had about 100 electrodes which could be implanted into the motor cortex. Okay? So then what's happening is when the monkey is moving from point A to point B, there are these 100 signals coming in, but you don't know what they mean. So we assumed that those signals have something to do with the endpoint coordinate of monkey's arm. So we put sensors here. So we knew at every instant what the endpoint was. And those signals, we put it through an artificial neural network and made it learn so that it could predict the endpoint with a certain, of course, correlation coefficient. So 70% of the time, let's say. So then once it is able to do that, now we can use that as a command signal and to control a robot within Duke, which was easy. And because the bandwidth was very low, we just, for the fun of it, we put it on the internet and controlled the robot in my lab. So which means by looking at what the robot was doing, I knew what the monkey was doing at Duke. Of course, if I just put a webcam, it would have been cheaper, but that's not the MIT way. So anyway, we were able to demonstrate that you could control. Now, is it just purely fun and games? No. The reason is that eventually, there are people with spinal cord injuries, quadriplegics, whose brain is perfectly fine, but their natural connection to the arm or the legs is severed. So by just like cochlear implants or heart pacemakers, eventually we think there could be neural chips which would actually read their thoughts and control, let's say, their wheelchair or a smart prosthesis, or even give them an arm 10,000 miles away. So that's the hope, and further work has been done. There is a whole area. Lots of researchers are working on this area. DARPA has been funding it, and there has been quite a bit of progress since that time. So what's then the provocative question there is that now that this is next level of interaction, so it is not only that you have these sophisticated information processing interfaces, but you have actually a chip in your brain or a way to access your signals, which hopefully will be non-invasive in the future. Then it is possible that the homunculus that I talked about, where the body representation is, that would include the robot as well as a third hand. Suppose I implant something like this into my brain, and I have both hands. There is a third robotic hand, which I consistently operate, which I send signals to, command signals to, and it sends back sensory signals to me. Then it is completely possible, based on what we know about cortical plasticity, that an area will develop in my brain which is devoted to that robot. So the robot now has merged with me, not only in terms of operationally, but also in terms of my own quote-unquote software. So it is possible that that level of integration will work. So as I said before, so there are these interactive technologies, but let me go to the next one. So once this level of integration happens, this is interaction level 5. The interaction level 4 was just me operating a haptic interface, which operated somewhere 5,000 miles away, another robot, and so on, which gave me basically superhuman capability in the sense that with just regular interfaces, without the brain-based interfaces, I could have superhuman reach, that is 3,000-mile-long arm, as I said, or I could even have super fast reaction time. That is, for example, when my brain commands my hand, the signals travel at most around 50 meters per second, so 30 meters per second, which means it takes almost 30 milliseconds for example, those signals to reach, or for the sensory signals to reach my brain. So I am essentially teleoperating, my brain is teleoperating my hand. Okay? Now, if I eliminate this path, but give an electronic pathway, that can be reduced considerably. It can be few milliseconds, so there is no time delay. So which means that a person with brain-machine interface could have much faster reaction time. Now, with brain-machine interface, what will happen, I think, is that this is the provocative question. Because it is integrated into the homunculus, maybe the definition of who we are itself will change. So there is the new self where the electronics and the interface is partly merged with our brains. So hopefully, maybe we can do plug-and-play skill acquisition. For example, we have a different software loaded, so we can play music, or you can do surgery, and then you take off that module. I'm speculating here. Then it can be, for example, it can improve your real-time simulation and modeling of data, all this complex data that our current brains are unable to understand. With the help, because we have now the resources of these processors which are interacting with virtual world while at the same time interacting with the real world. So with the system together, it is possible that we can understand these worlds much better. And then, so we can even perhaps live comfortably in abstract spaces that are higher than 3 dimensions, or if you count time, 4 dimensions. Perhaps these are possible. I just speculate at this point. So I think, as I said before, that with all the even current technologies and speculating a little bit, through human-machine integration, we can have superhuman capabilities which in fact enhance our body functions, that is like reach and reaction time, but also through continuous feedback between the two, that we can have evolution of the mind as well. Thank you very much.
You mentioned that for very long distances to handle the time lag, you used some predictive algorithms. I was wondering, what does it feel like when you find out that you were wrong about what your hand did?
Right.
And I guess sort of speculating, level 5, what would happen, or how would you modify your memory then at level 5?
Yeah, so I mean, these are clearly not a lot of research, at least we haven't done a lot of research in those. But for example, NASA has this real problem when they have to operate through their robot on the space station, because they have to move a little and then wait for it to happen, again move a little, because they don't want to bump into anything. So unless you have a perfect model of that environment, and you have a perfect model of the control scheme, and there is no noise and so on, only then that this will work perfectly. But the counterpoint is that, as I said, even in our real world, that our hand is being teleoperated by our brain, because there is a 30, 50 millisecond time delay between the two. And the way we cope with it is by slowing down. So if you slow down the bandwidth of your actions, so hopefully the errors that you commit will not be serious. And especially if the environment is a kind of low impedance environment, the forces due to errors will not be high, so you won't break anything.
Hi.
Hi there.
Hi. I have a background in AI, and I'm also a touch therapist. And I haven't really put these two things together in a technical way, but I have tried to integrate them in computational models of mental state, looking at sort of the boundary between appearance and reality, or perception and reality. And I was just wondering, I mean, it seems like you are coming up to that edge, especially in the beaming application. I was wondering if you've given any thought to the idea of an architecture that might actually take an aspect of mental state into account to give semantics or augmented semantics to the objects.
Right.
The subjective experience of objects, if you will.
Right. The thing is, beaming project has just started, and also there are many partners, and I'm not the AI person in there. Mainly I am the robotics end of things, and there have been discussions about the kind of topics that you mentioned about. I can certainly give you pointers to who may be the best person to talk to.
It's a very exciting area.
Thank you. Yeah.
Hi. What do you see are the implications of haptics on the future of human-computer interfaces?
I mean, I hope that it will be as common as visual and auditory interfaces today. But we face real problems. That's why I said I can't relate to these scenarios of singularity and the machines exceeding us, because in this we haven't yet achieved what is the equivalent of the VLSI revolution in mechanical things. And we have no way of kind of controlling forces at a distance. So until our actuators can improve a lot and their mass to energy ratio decreases quite a bit, and their size. For example, as I said, I can mimic touching through a tool because I only need to mimic a force vector. And that's how, if at the tip of a tool, there is only a force vector. Whereas if I want, the holy grail of the field is to have a glove, let's say, where I can wave it in my hand and I should be able to feel any object that I program. But in order for that to happen, I need to have essentially mechanical equivalent of televisions at each fingertip, which 0.5 millimeter to millimeter sized motors, hundreds of them in each fingertip, each of them under program control, and they should all be massless. And they should violate some laws of physics, like reaction force somehow has to be taken into account. So anyway, there are some issues in terms of both technological development and as well as how to circumvent. Now, people have tried electrical stimulation, people have tried various things, and I usually get asked, oh, why are you bothering about all these motors? Why can't you just put a helmet and just stimulate the somatosensory cortex? Yes, sure. If we know how to do it, yes. So the thing is that if we can overcome limitations such as these in terms of spatio-temporal display of tactile signals, I think there is a very bright future for haptic interfaces. Okay, thank you.